Okay, I promise we're getting to the good stuff, but first we have to cover two more chapters that are important for understanding how the PIC works on the inside. First is Chapter 5 that we call Space and Time. So what we'll discuss right now is how does our C code get translated into machine code and stored on the PIC, and how much space does it take? And then how long does it take that code to run? Specifically, if we want two actions to occur, can we control the timing between them to get really accurate, precise timing? The reason why we care about these two things, so the amount of space that it takes, we need to know, are we going to run out of RAM? Do we have enough space to store all of our variables? And do we have enough flash to store our program? Or the opposite of that, are we using not all of the flash on the PIC? And if we're going to go into production with a piece of hardware that we built, are we paying too much for our PIC because we have too much flash and we'll never use it? So could we downgrade, go to a PIC with less flash memory so that it costs less to make? So the goal here is to write some C code, turn it into assembly code, see how long it's going to take to run, see how much space it takes up on the PIC, and then see how the compiler helps us do those kinds of things. So the compiler is going to help us. We have Xc32 Tools, and we've seen a couple of them so far. Of course, we have Xc32-GCC, that's the compiler. We've seen the NM program that takes processor.o and turns it into a big list of addresses for the SFRs. Now we'll see some other kinds of tools, and these are things you'll find in other tool chains as well for ARM microcontrollers and that kinds of things. But we're going to generate two kinds of files, a map file, so a .map, and this is a report on memory. It's going to tell us where in memory all of our code was put, so the specific functions, where they went, and then an estimate of how much RAM we need, and not at any given time, but how much RAM we can see gets turned from not being used to being used as a function is called, and then being freed up again. And then a .dis file, that stands for disassembly. And this is a kind of a neat file that takes our C code and interlaces it with assembly code. The cool thing about assembly, of course, is that every line of assembly should take one clock cycle to run. So we'll see that maybe a few lines of C get turned into many lines of assembly, and then we could just count how many lines of assembly there are and get a rough estimate of how long it takes, say, a loop to run or our main file to go from the top to the bottom. Now, the compiler is actually giving us some options for not only making these files, but how well it makes our code, our C code, into the code that runs on the PIC. And that's called optimization. When you say that programming is like a language, well, how well does that language you write in get turned into these two things, into the space that it requires to be stored and the speed at which it runs? So our compiler, when we run it, we get to tell it actually which kind of optimization to use. Should we optimize so that it takes less space so that we can get more code into the same PIC? Or should we optimize for time so that our code runs faster? And those two usually play off each other. Sometimes to get our code to run faster, the compiler will turn it into more code because it has to do less things like jumping around that waste time, and it can just run more linearly, but it takes more space to do that. And other times, we want our code to fit into less memory so that we can buy a cheaper PIC, but then it might run slower because there's more interpretation that has to happen. So those are the trade-offs. And the Xc32 compiler gives us 5 levels of optimization. And Microchip really wants you to pay for the more advanced ones. So we get 2 of them for free, and then there are 3 more that if you're doing some production code, you could pay them like $1,000, and they would unlock your compiler. They would give you a new version of the compiler so that you could then do better optimization. So the 5 levels, the level 0, which is the most basic, is no optimization. And we never do that, but we're actually going to do that for this specific chapter so that we can see how the compiler works with no optimization. That's the straightforward way. Then there's like what we call, so this is level 0. Then we have level 1, which is slightly faster and smaller. So this is like your basic bare minimum amount of optimization. This is what we compile with our makefile. Then we have a better version of that. That would be level 2. So can we just make it go a little bit faster and a little bit smaller? And then the next ones we have are specifically smaller at the sacrifice of speed. I think that's level 4. 0, 1, 2. This would be level 3. And level 4 would be faster or something like that. We'll discuss those in theory, but we won't get to see them because we don't have those in our free version of the compiler. But today what we'll do is we'll compare the no optimization level to the basic optimization level. So we have these reports, how big our code is and how fast it should run by just counting the lines of code. But usually, you may not believe this, and occasionally the compiler might throw in a couple of delay statements and it's not quite sure exactly how long our code is going to run. So how do we actually physically time our code rather than just relying on counting, from these reports? Well, one way is to use an LED or a pin, and in our code, let's say we have a function, we want to know how long the function takes. Before that function, we would make the pin go high, and then the function would run, and then after the function, we would make the pin go low. Each of those lines of code hopefully take very, very small amounts of time, tens or hundreds of nanoseconds. Compared to the code we're trying to time, maybe it takes a lot longer. And then we could look at that on an oscilloscope. Or if it's long enough, we could actually look at the LED and time it with a stopwatch. But the oscilloscope would show a voltage that goes from 0, and then it goes high, and that's when our function runs, and then it goes low. And then we just need to know how much time it took. So this is why sometimes it's helpful to have an oscilloscope, because maybe we see literally how long it takes. A lot of times, though, what we would do is we would have our code run, say, 10 times in here, though, because we might have a piece of code that runs very fast, maybe, microseconds worth of code, and that's still pretty hard to time even with an oscilloscope. So we might have our pin go high, then in a loop we might have our code that we're trying to time run 10 times before the pin goes low. We would take that time and divide by 10. Okay, so that's one way to measure how long things take. The other is that the PIC can do the measurement itself. So we have timer peripherals. So these are built-in functions on the PIC that keep track of time. Now, specifically, we have 5 timers that come from Microchip, but we also have what's called the core timer, which is part of our CPU. We've talked about how the CPU has registers, and the registers have special functions like adding and subtracting and division, whatever, the things that the CPU is good at. Another thing that our MIPS 32 processor inside of the PIC has is this core timer, which is a 32-bit number, unsigned, and it does a +1 every 2 sys clocks. So when our PIC is running at 80 megahertz, the core timer goes up at 40 megahertz. That'll be important to know because we'll read that number, and depending on how much it has changed, we can use the fact that it takes 25 nanoseconds for that number to go up by 1, and then we can time our code that way. So in the same way that we used a pin to figure something out, what we can do now is we can make a variable, an unsigned int, and make it equal to the value of the core timer, let our code run. Then when the code is done, we will read the core timer again into another variable, we'll subtract the 2, and then we can use the fact that every increment of that number is equal to 1 over 40 megahertz. So let's take a look at some of this code. Let's see, I think the first thing I want to do is explore our folder structure and make a new project. We'll run off of our Chapter 5 example code. So here in Chapter 5, Time and Space, I'm going to copy timing.c, and we'll do some experiments on timing.c. And I will take my skeleton folder and copy it and paste it. I'm going to rename it timing. I'm going to drop timing.c in there. And now I've got my make file and all my support files ready to go. We'll go take a look in Visual Studio Code. So here's my timing folder, and here's timing.c. We'll run through this one line at a time. First, let's take a look at our make file. Our make file, the only thing you had to change was this stuff at the top, but inside of these are the essentially what's called when you call the program make. And there is this line here called C flags on line 80. And these are extra tags after you call GCC that get added. And this one is the letter O and then the number 1. That says when you compile your code, use optimization level 1. So right now, I'm going to change this to optimization level 0. We're going to compile our code, see what happens when there's no optimization. Then we'll come back and change it to 1 and see what changes have been made. Also in here we can see here's the performing the disassembly step. So adding the -s says make our disassembly file, and where's our map command? I'm not seeing it right now, but also in here is a similar command that says make our map file. Okay, let's go back to timing.c. So we start by including nu32.h. That gets us Xc32. That gets us the .h file for our specific PIC, which gives us the names of all the SFRs, that kind of stuff. We have a pound define, so anywhere we find the word delay time, we're going to replace it with the number 50 million. We're going to have a function called delay and toggle LED. Then we get into main. Every time we're using the nu32, the first thing we'll do is we'll call it nu32 startup. That just tells the cache to turn on, makes the PIC try to run as fast as possible, initializes our LEDs and our buttons, that kind of stuff. And then this is pretty easy. We've got an infinite while loop. It's going to call the delay function, and then it's going to toggle the LED. So this should just blink a light. So the delay function says, let's have a for loop. We'll go from 0 to 50 million. Every loop will add 1. And then we'll call toggle LED, and we will invert on lat F, so our 2 LEDs. Remember, 2 in binary is let's see, 0, 1, 2. We're going to be inverting F1 because this is the same as 0B1, 0. So we're always going to be inverting. This would be F0. So here is F1. So this is just a program that all it does is blink F1. How long does it? What's that rate of blinking? So how long is it on and how long is it off? Really depends on how long does it take the PIC to do this for loop, start at I = 0, and add up to 50 million. And you might think, well, the system clock is 80 million, so hopefully it only takes like 1 clock cycle, to add 1 to the I number. So this should happen, roughly like a little less than a second to be off, and then a little less than a second to be on. And we could run this code, and I'll let you do that. Put this on your PIC and use a stopwatch to see how long it takes that light to blink. But let's compile this code and take a look at the disassembly to figure out how long we think it could run just by counting the assembly lines. And we'll talk a little bit about assembly. Okay, so that's saved, and the make file is saved. So let's go over to our terminal window and just make sure it's there. So I'm in my root folder, and I will cd into timing, and I can see what's in there, all those good things. And because I'm on Windows, I'm doing min gw 32-make. Okay, so this line, we can see the -G, the -O0 for optimization level 0. Making my O files, it's linking them. There's the command we could see. So it looks like it's the linker that makes the map file. So the compilation process earlier probably made the disassembly file, and then the last step in the linking made the map file for us. Oh, here's a disassembly. That happens at the very end. So let's do a dir again. We can see all the files that were made. Here's our disassembly file. That's going to be the assembly we'll look at. And then later we'll look at the map file to see how big our code is. So we'll switch back to Visual Studio Code. I'm going to open up this .dis file. And we can see this got pretty long. How many lines? We've got 1,000 lines for main.c, which didn't have nearly as many. What did main have? Timing.c only had 26 lines. So the disassembly is a really thorough management of what's going on. And this is going to list a lot of things according to the memory address that functions were assigned. So let's not worry too much about that now. But here you can see hard-coded memory addresses. And then at that memory address, here is the data that was put there. And this, of course, isn't binary, so we don't necessarily know what this means. But some of the sections will make a little bit more sense than others. The previous chapter, the homework, talked about resets and what happens when the PIC turns on. And in homework questions, you got to think about those kinds of things. Here we can see exactly what happens. On reset, this is the address that the PIC starts at on reset. And here's the command that happens. This is the address. This is the value that's at this address. And then here is the non-binary version of that that says we're going to run this assembly line command, JAL, and the input to that function is this number, which looks a lot like an address. And then once that line is run, we're going to do an NOP, or NOP. Now, if we weren't programming C and we were programming directly in assembly, you would have to learn all of these different assembly commands. And that's why we don't do assembly, because it doesn't read very much like English. Our C code is a lot more compact, as we'll see in a second. So you don't need to know what all these are, but a few you should know. So anything that starts with a J generally means jump. So jump says jump from wherever we are right now to this new address. So on reset, we're going to jump to this new address, and we could go find that. Of course, they put it right here after us. And any jump command usually takes 2 clock cycles. So this is one of the few assembly line commands that doesn't happen in one step, it takes 2. So immediately after this command, we have a NOP command. That stands for no operation. Basically, it said, I know that a jump just happened, so I better wait a whole nother clock cycle before I try to do anything else. So we jump to this address, and we start doing these things. Okay, I don't know what there are, but here's a jump again to K0. K0 is probably the name of a variable. So hard to tell exactly what's going on here, but this is all the initialization code that happens. And probably every single piece of PIC code we write has all this stuff copied exactly the same. Nothing really changes. So what we want to do is we want to find out where's main, like where does our code start? So I'm going to do a Control F and look for main. And here we start to see the disassembly of main. And so this disassembly file, it's taken the original C and it's now kind of interlaced every line of C with what it got turned into in the assembly code. So here's int main, and its first memory address is this memory address. And the first thing it does is it does an add command. And you could probably guess add IU is probably the unsigned integer. So add two 32-bit numbers. And then swap is move some memory around. And then move is move some memory around. So we get these math functions that are happening. And then we haven't even hit our line of code yet, right? So just the fact that we called the function main made 4 clock cycles occur that did some stuff. Then we finally call the NU32 startup function. Well, the startup function isn't right here, it's somewhere else in code. So there's going to be a jump. And we'll jump to this memory address, which is where the NU32 startup function exists. And then there'll be a NOP because every jump takes 2 clock cycles. So when we go there, we'll go find that startup function. We'll see that when it's done, it's going to jump right back to this position again so that we can keep going down in our line of code. So we'll jump to here. So I'm going to take this address, I'm going to copy it, and I'm going to try to find it. So down further in the code, here is what the NU32 startup function does. So it looks like every time you go into a function, it does 4 lines of code. anything that says SP is a stack pointer. If you're familiar with the stack pointer, it's basically just reorganizing the RAM to say, okay, now we're somewhere else in the code, so we better have a pointer that reminds us where to go back when we're done. Okay, inside of this function, we called this function built-in disable interrupt. It did this stuff. Then we have this function. It does this stuff. Notice that there's no jumps in here, so we could basically say this function built-in MTC0. It takes 4 lines of assembly, so it takes 4 clock cycles, or 4 times 1/80 megahertz seconds. Okay, here is the manipulation of a special function register. So to change this special function register, the fields in here to this value, that one line of C actually takes 1, 2, 3, 4. It took 5 lines in assembly. So when we are trying to figure out how long our code takes, we can't really look at the amount of C code, because each line of C might get turned into sometimes only 3 assembly lines, sometimes 5. It might be many. So we can't just count the lines of C. We have to look at this assembly to figure out how long some code will take. So this one line of C code takes 5 clock cycles. And we just keep going down. This is all the initializations that happen in NU32 startup, turning on the UART and all that kind of stuff. Here's the very end of the function. And when we're done, we're going to jump back to where we came from and then do that no op. Okay, so we're back to main. We've initialized. We get into the function delay. We're going to jump to our delay function. When we're done with that, we're going to jump back to our toggle function, and then the infinite loop says jump back to here again. So we're just stuck in this infinite loop, calling this delay function, calling toggle light. So here's what we really care about. How long does delay take? The delay function is right here. So in this function, in the C code, all we have is a for loop for I is 0 to 50 million. And when we first get into that function, we saw that every time we go into a function, it takes a couple lines of assembly. And then here, to do that, here is our for loop. The for loop with no optimization is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines. So what I was hoping for was just saying that I equals I plus 1 would take maybe 1 clock cycle. Really, it takes 12. And something that I thought was going to take about a second probably takes more like 10 seconds. Then when that function is done, we've got a couple more lines before returning. And here's toggling our light. We get into the functions. We've got this stack pointer manipulation stuff. And then we've got one line of C, which is the actual atomic manipulation that says, please flip this bit for me. And here we see it takes 3. So what we were hoping for was it takes 1 clock cycle to make an LED invert. Actually, it takes 3. So let's do one thing here. Let's compare using this atomic manipulation, which is a little hard to read and understand, and use the more straightforward lat f bits equals not itself, and just see how much worse it makes it. How much longer does our code take? It used to take 3 clock cycles. Let's see what it does now. I'm going to jump back to the command window, and rather than just making here, I'm going to make sure that I'm starting clean. So instead of just making, I'm going to say make clean. And I see that when I do a make clean, it deletes all of the files that had been made in the last compilation process. So it deleted the old dis file and the hex and the map and all the .o files. Because I've made some slight changes here, sometimes the compiler doesn't realize I've made changes. So I want to make sure I'm just starting clean. So we're starting again, and we'll remake. Okay, and we'll go back to our disassembly. And we're going to try to find a delay. So the delay hasn't changed. I didn't change that. I changed the toggle function. Here's the toggle function. And when we did the atomic bit manipulation before, it took 3 clock cycles. So using the latf bits command takes 1, 2, 3, 4, 5, 6, 7, 8, 9. Takes like 3 times longer. That's too bad. So the 2 different ways of doing the exact same thing, one actually takes a lot longer to have the PIC do it. So there is definitely advantages to using latf inv and set and clear as opposed to latf bits dot something equals something. But this was all with our optimization level set to 0, which was no optimization at all. So let's quickly go back to optimization level 1 and do a quick comparison just to see how the compiler hopefully helps us by optimizing. Okay, we'll do a make clean. Make again. And then the last thing we'll do is take a look at the delay. Okay, we go back to our dist file. We find toggle. Ooh. For delay. Delay. Toggle. Okay, this was 9 before 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the our optimization didn't really help here. But one thing that is missing is at the beginning of every function we saw before had some stack pointer manipulation stuff. That seems to be missing. So our function did get a little faster because we're not doing any manipulations. And then let's look at delay. So here's delay. And we've got 3 initializations here. That probably has to do with like making this variable I. And then our for loop, which used to take something like 12, our for loop has been turned into 2. So the optimization level here has gone through and really cleaned up our for loop. So not very predictable. Some functions were really affected, like the for loop, and others were not, like this special function register manipulation. So when you're specifically trying to find out how long it takes your code to run, this is one way to find out. Look at the disassembly. While we're here, let's take a look at this map file. The map file is kind of a parallel to the disassembly file. It's going to show a whole lot of memory addresses and summing of things. So as we go down from the top, we've got our PIC32 memory usage report, and we have a .text section. So this is our code. Our code, the length of our code in PIC memory is taking 452 bytes. And remember, we have 512K about. So this is taking 0.3% of our total amount of memory. So we, obviously our code could be much, much longer. We'll probably never write a program that takes anywhere near all of the memory on the PIC. But if you looked at the PICs and you saw that the same PIC with less memory costs a few dollars less, you could save a lot of money if you make a million units of something. If each PIC is a couple dollars less, you save a couple $1 million by using the PIC with the correct amount of memory. So using this map file is very important. 5 minutes. We can also see, so these are the different sections, ksec0, ksec1. That's our flash memory. Here's our dynamic memory. This is our RAM. So RAM that we have made, like variables in main that always exist, those would be on the heap. So here our code never declared a variable, so we didn't have to reserve any of our RAM memory permanently. All of it is what we call on the stack. That means a function that needs a variable can pull from this memory to exist, and then when the function's done, that memory gets deleted and pushed back into the stack again. So the sum of the stack and the heap should be the total amount of memory. And notice here that while we say we have 128K RAM, we've actually got 131,032. So this is actually the correct definition of how much memory we have, not like the the sales representative saying, you have 512K and 128K. Here we can see the actual amount of so other stuff you could find in here. Let's look for, say, our delay function. Again, it will tell us the memory address of where the delay function lives, toggle and main. So we can specifically try to find, if I don't know why you would ever really be interested in this kind of stuff, but where is our code stored and how much, let's see, does it say how long, like how big the functions are. I think in here we can also see how big the function are. For example, here's the start of the delay function, here's the start of the toggle function. The difference between those two is probably the length of that function. But I think somewhere else it also says. Okay, so this was timing basically because we were looking at that infinite delay, with a while loop. Let's say we wanted to do a more specific, exactly 1 second delay. So let's write this code to do exactly 1 second delay. Now we could do some guess and check using a for loop, looking at the map file, looking at the disassembly, count how many lines it takes, go back and forth, kind of twiddle with it until we get that amount. Let's instead use our core timer. So the core timer is that 32-bit unsigned number that's in the PIC. As soon as the PIC turns on, that number starts to increment at 40 megahertz. You can't stop it, but you can change the value. So if we say CP0, I'll write it down because I always forget. Set count. Inside of the parentheses here, we get to put any unsigned 32-bit number. So let's force the core timer at this moment to go back to 0. And then we could say, what we want to know is the core timer getting to 40 million? Because if it gets to the value 40 million, that's how long it takes it to count to 1 second, because it's counting at half the 80 megahertz that the system clock is, so it's counting at 40 megahertz. So when it counts to 40 million, we get exactly 1 second. So we'll have a while loop. Let's have a while. We'll do the CP0 get count function is less than 40, 1, 2, 3, 1, 2, 3. While it's less than 40 million, let's do nothing. So we'll set the count to 0. We'll look at the count. At probably this moment, the count is like 2 because only a few clock cycles have passed. 2 is less than 40 million. We'll come into here. We'll immediately check what's the count now, and what's the count now, and what's the count now, and we'll go that over and over and over again until we hit 40 million. After that, exactly 1 second has passed. So that's how we can get any kind of delay with really fine resolution. We could do 25 nanoseconds of resolution, plus or minus a few clock cycles, because if we now turn this into a disassembly, we'd probably see that there's a couple random stuff above and below all these C lines. But we can see exactly how to get really fine timing using the core timer. Note that this function starts with an underscore. An underscore is usually a special function that the writers of the compiler have given us. Here, what they're trying to tell us is that this is a function that doesn't act on a PIC peripheral. This is part of the CPU. CP0 is a core register. That's part of the MIPS processor. What we'll see soon is that the PIC has other timers, and those functions won't start with underscores. Well, we're going to write our own functions for those, manipulating the SFRs. But this isn't an SFR manipulation. It's a little bit more complicated than that because it's manipulating a core register. So that's a good intro to Chapter 5. We looked at the disassembly file mostly. We took a brief look at the map file. We looked at this optimization. So remember, you're going to change the optimization level in your makefile specifically for this chapter to level 0. When you do the homework for this chapter, it's got to be in optimization level 0 because the optimization, and you'll see this, sometimes wipes out whole things. If you declare a variable or if you have a for loop that doesn't do anything, optimization level 1 sometimes removes an empty for loop because says, oh, that for loop doesn't do anything, I'll just delete it. That can be harmful if we wanted a for loop to be there and kind of eat up time. Whereas optimization level 0 doesn't delete anything. So for only chapter 5, remove the optimization. But remember, when we go to chapter 6 and all of our future code, we want to use optimization level 1 because it does help a lot in making our code run faster.